Today, I would like to talk about the Karnaugh map. And this is the outline of this presentation. So I'll talk about Boolean function minimization. I'll talk about the Karnaugh map. We'll see 2, 3, and 4 variable Karnaugh maps. I'll talk about prime and essential prime implicants, minimal sum of products, minimal product of sums, don't cares. There are more topics in this presentation about 5 and 6 variable Karnaugh maps. However, I'm going to skip the 5 and 6 variable Karnaugh maps. They are not really included. And finally, there is the multiple outputs. So I'm going to cover all of these topics. So this might require, 2 or probably 3 lectures. So I'm going to start today talking about the Karnaugh map, introducing the Karnaugh map. Right. So what we have seen is that we have seen Boolean algebra, and we have seen it in quiz number 2. And we can use Boolean algebra to minimize, the equations. So the complexity of a Boolean function is related directly to the complexity of the algebraic expression. So the truth table, defines the function uniquely. However, the algebraic expression is not unique. You can minimize the expression to get another expression, which is equivalent, but you can get different expressions for the same function. So the truth table is unique, but the algebraic expression is not unique. So we can use as I said, we can do algebraic manipulation to minimize the expression. But the problem with algebraic manipulation is that it depends on experience. So sometimes, if it is really simple enough, and when you are dealing with 3 variables, 4 variables, you can guarantee, with some experience that this is a minimal expression. But in general, it does not really guarantee that. And this also depends. So it depends really on experience. However, I'm going to show you in this presentation, I'm going to show you how we can use the Karnaugh map technique to guarantee that your expression is minimal. So we can guarantee that with the help of the Karnaugh map. So the Karnaugh map is really easy to use. Once you understand it, it's really easy to use. Right, let me start with a simple example. That's a function f. It's a function of 3 variables. And these are the minterms. You can see we can focus here on the 1 entries. So we have this one, this one, this one. And I have 2 more here. So we have minterm 1, minterm 2, minterm 3, minterm 5, and minterm 7. So these are the 1 entries in the truth table. And we can write the function f as the sum of these 5 minterms. Do you agree? Already we have seen this before. And I can write it in sigma notation. That's here my, what's this really happening? Just 1 second. Give me 1 second. So these are my 5 minterms in sigma notation, and I can write it algebraically like this. So when you write it, any function, you can just look at the 1 entries. You can see what are the minterms. You can write it algebraically. In this example, we have 5 minterms, and each minterm has to contain all the 3 variables, either complemented or not complemented. And you can have the prime or no prime. That's basically what it means. And because we have 5 minterms and each one has 3 literals, so we have 15 literals in total. But this expression here is not minimized. 15 literals, it means that the circuit will be large. So the question is, can we simplify this? Of course, we can simplify it. And if we can simplify it, we can reduce the cost of the circuit. That's really the purpose of minimizing the algebraic expression of a function. So what we can do is that we can do here algebraic manipulation of this. So I'm just copying the sum of minterms from the previous slide. So this is my sum of minterms for the function f. So let me take all of this expression and rewrite it here. So what I really need to do is I would like to simplify this expression from 15 literals and try to minimize it to a minimal, let us say, sum of product expression. So the best way to do to minimize this is to look at terms that differ by one variable. For example, this is x prime, y prime, z. So I have x prime z. Here I also have x prime z. Here I have y prime. Here I have y. So this can be easily simplified. Similarly here, I have, okay, if you look at these two, I can easily simplify because they only differ by, here I have y prime, here I have y, but they have the same x and z, okay? Okay, clear? So this is my strategy starting from a sum of minterms. It's not really that difficult at all. Already we have done this. Let me switch these two terms and let us combine these two. So you can see this is actually x prime z, and then we take between parentheses y prime or y. Here we have xz, and we take between parentheses y prime or y. And you know that y prime or y can be simplified to 1. So therefore, now we have simplified this to x prime z. Here I have simplified to xz. So we have reduced the number of literals. We started with 15, now we are at 7. This is good, but we can do better than this. Now, again, you can see that this x prime z and xz, they have the same z. So they differ in x. So I can just combine them and simplify. That will be very easy. So let me bring them together. And here I have x prime or x, which is equal to just 1. So this can be simplified to simply z. Okay? So that's equal to z. Again, I need to clean up. Okay, so you see that we have simplified it. Now we are at 4 literals. But again, we can do one more step. Can you see this last step? Can you see it? Okay, can you tell me what it is?
Simplification theorem.
Yes. So we can get rid of what?
Z prime.
Yes.
Exactly, of z prime. Thank you very much. So I can really get rid of this z prime, and we are done. Okay, so that's basically the simplification theorem. But if you would like to apply it, I can use the distributive property as shown here. And basically, we can, it's a bit slow. It's actually just, okay. So there is a lag. Anyways, so we get, at the end, we get 3 literals. Now, by just observing this function, you can see that it is minimal and it cannot really be simplified. The variables are different. So we have z, we have x prime, we have y. Khalas. We cannot do anything about it. That's good. So we started at 15 and we ended up with only 3 literals. This is really good. Okay, so that's algebraic manipulation. Now, the drawback of algebraic manipulation is that there are no clear steps in the manipulation process. So therefore, there is no algorithm that can tell me that, okay, which terms should be grouped together. And you have choices. You could have done it differently. So it does not always guarantee that you will get a minimal expression at the end. And if you have combined the terms differently, you might not really get the same result. You might not get a minimal expression. So this is why algebraic manipulation, because the steps are not really clear, and you have to use intuition, okay, which terms to group them together, okay, which theorem to apply. So you can use different steps, and these different steps might lead to a different non-minimal expressions. But the goal here is to minimize a Boolean function. And therefore, we would like to reduce the number of literals to a minimum. And if you use the literal count, that will be a good indicator of the cost of the logic implementation. So we were able to reduce that to only 3. And that was really good, because the number of transistors that will exist inside the circuit implementation will be proportional to the number of literals that you have in the expression. So what do we do in the case of logic minimization. There is a technique, okay, that was invented, and this technique is called the Karnaugh Map, or K-map for short. So K here means Karnaugh. And this was invented a long time ago. And the Karnaugh map is still being used until today. You can easily use it, okay, even by hand, okay, to minimize functions. Let us say if you have functions of 3 or 4 variables, you can easily, okay, use the Karnaugh map to obtain a minimal expression. So that's really very simple and very easy. So what we do is that we draw the Karnaugh map as a diagram, which is made up of squares. And basically, it's the same thing like the truth table. So we just copy the function from the truth table into the Karnaugh map. So each square in the Karnaugh map will be like an entry in the truth table. So it will be a minterm. So each square, you can actually put either a 0 or a 1. And if we draw the Karnaugh map in a way so that adjacent squares differ in the value of one variable. So this means that we can combine adjacent squares. This is really the idea of the Karnaugh map. The idea is to combine adjacent squares, and by combining adjacent squares, we can simplify the expression. So we can derive easily the simplified expression directly from the Karnaugh map by just visualization. Just look at the Karnaugh map and combine adjacent squares and simplify. That's it. We can obtain different expressions. I can obtain a simplified, a minimized sum of product expression. So this will be an AND OR circuit implementation. It is sum of products, which is minimized. Or we can obtain a product of sums. Yani we can use the same Karnaugh map to obtain a different expression, which is a product of sums, which will be an OR AND circuit, a 2-level OR AND circuit. So we can obtain both of them from the Karnaugh map. Okay. So I'm going to show you now how to draw the Karnaugh map. I will start with 2 variables, then we'll move into 3 variables and 4 variables. Okay, maybe 4 variables next time in my next lecture. So let us start with a 2-variable Karnaugh map. So now the minterms, if you have 2 variables, x and y, you will have 4 entries in the truth table. The Karnaugh map will be the simplest in the case of 2 variables. So here I have variable x, here I have variable y. So we have a 2 by 2. So each variable will have 2 possible values. So x can be 0 or 1. Y can be 0 or 1. So we end up with 4 squares inside the Karnaugh map. And these are the 4 entries that exist in the truth table. So notice that where are the minterms? So here I have minterm 0. This is for 0, 0. This is minterm 1. This is minterm 2 and minterm 3. And these are the algebraic, okay, terms. Okay, so you can write it for each minterm. So this is my 2-variable Karnaugh map. It's very simple, very easy. Now, from the truth table, you can construct easily the corresponding Karnaugh map. Let us start here with the truth table. So this is my function f. In fact, you don't even need a Karnaugh map for 2 variables. You can, with some intuition, you can actually get the expression directly even from the truth table. But just to use this Karnaugh map to show to you how we can use this. So what you need to do is that you need to draw the Karnaugh map. Notice that we have 0, 0. So this is x equal to 0, y equal to 0. So this is entry 0, 0. So that's the 1. I'm going to just to copy it here. This is a 0. That's for 0, 1. I'm going to copy it here. And here I have 1, and here I have 1. So these are here and here. So first, what we have to do is that we have to copy the 0s and the 1s entries of the function inside the Karnaugh map. This is very important. Okay, is this clear? So make sure that you copy each value into the proper square inside the Karnaugh map, because if you don't do so properly, you lose the question. You get 0. Okay, and you have seen this again and again in quizzes. Small mistake, you destroy your question. So we don't really want to do this. So copy the function values into the Karnaugh map inside the squares property. Do not make any mistake. Fine. So now what we need to do is that once you have copied these, okay, then we need to minimize. So we have the Karnaugh map, and these are my minterms. You can see this is minterm 0 here. This is 0, x, y, 0, 0. That's actually is the square. This is minterm 0. This is x, y equal to 1, 0. That must be minterm 2. And this is minterm 3. Okay. Now we can always write the expression as a sum of minterms. This will be the canonical form. Okay. So 0, 0, we get x prime, y prime. Okay. Minterm 2, it will be x, y prime. And minterm 3 will be xy. So this will be 6 literals, and it is not minimal. So the idea now is to combine adjacent squares. So how do I combine adjacent squares? Well, these two squares here vertically can be combined. These two horizontal squares can be combined. So let us combine these two, okay, vertical squares. So if I combine minterm 0 with minterm 2, these are the two vertical squares. So one is so this is minterm 0 and or minterm 2. So when you combine these, you get x prime, y prime, or xy prime. Now notice they differ by the value of a single variable. So notice it's the same y prime, but x is different. So we have x, we have or x prime, and this can be simplified to 1. So therefore we get y prime. So by combining these two adjacent squares, we can simplify the term. So we got only y prime. I combine these two horizontal squares. So these are minterm 2 and minterm 3. So we got minterm 2 or minterm 3. Of course, they have to be ones. So they have to be both 1 and 1 in order to combine them. You cannot really combine 1 with a 0. You have to combine 1 with a 1. Okay, clearly. So when you combine minterm 2 with minterm 3, now look at minterm 2. This is the term xy prime or xy. Notice it's the same x. So they differ only in y. So notice that x here is equal to 1, but they differ in y. Okay. So you can simplify it and you can actually get x. So it does not really depend on y. So you get x and between parentheses y or y prime is simply equal to 1, and therefore you get x. In fact, you can look at the Karnaugh map and you can see, let me clean up things here. So if you look at the Karnaugh map, now here you can see for minterm 0 and minterm 2, the only thing which is in common is y equal to 0. So this is why we wrote y prime. X can be 0 or 1, it does not really matter. In the case of this blue box, so we are combining minterm 2 with minterm 3. The only thing which is in common is x equal to 1. The value of y can be either 0 or 1. So this is why it is x. So we can get it directly from the Karnaugh map. Okay, that's what it means. Muhammad, yes, you have a question?
Sir, in the Karnaugh map, I either do the vertical square or the horizontal, or do I need
yes,
to do
yes,
both?
you can actually combine vertical squares, you can combine horizontal squares. So I will talk more about how to combine squares maybe in my next lecture because I'm running out of time. Okay. I will show you a lot more examples, okay, many examples. I will show you many examples to understand how this can be done. Okay. So now by combining this, we can say that now the final, okay, if I would like now to show here the final expression for f will be x or y prime. That's it. That's my expression for f. This is now my simplified expression, and we're able to reduce it to only 2 literals. We started with 6 here when you look at the sum of minterms, and we simplified this to only 2. Okay, with the help of the Karnaugh map. So in the case of 3 variables, here I have 3 variables x, y, z. You can see this is x here. This is y, z. So in the case of x, we have only 2 values, 0 or 1. So these are 2 rows inside the Karnaugh map. And in the case of YZ, we have 4 columns because we have 4 possible values of Y and Z. So these are 4 columns. Now notice that the last 2 columns are numbered as 1, 1, 1, 0. This is always the case when you are dealing with midterms. So make sure that you have column 1, 1 before column 1, 0 in this order. Okay, and if you put them in a different order, then this will be wrong because you cannot simplify. So the 2 adjacent columns here have to be differed by the value of a single variable. So notice that next to 0, 1, we place 1, 1. We don't place 1, 0 because 0, 1 and 1, 0, they differ in 2 values, in the value of Y and the value of Z. Is this clear? That's very important when we draw the Karnaugh map. Okay, so you have to make sure that the columns are not in a numeric order. They have to be 1, 1, then 1, 0. So now what you need to do is that you need to fill the midterms. So we have 3 variables, x, y, z. So this is 0, 0, 0. So this must be midterm 0. Then you have midterm 1. Now notice that the next one is 0, 1, 1. So 0, 1, 1 is midterm 3. And then you have 0, 1, 0. So notice that in what order the midterms are written inside the Karnaugh map. And then we have 1, 0, 0. This will be midterm 4. Then 1, 0, 1. Notice that 1, 1, 1 here is midterm 7. And then we have midterm 6. Okay, is this clear? This is very important. We are going to use this, okay, when we simplify 3 variable functions using the Karnaugh map. And you can, of course, write for each one, you can write algebraically. This is the algebraic term, okay, for the midterm. Okay, so this is the midterm algebraically. Do you have any question about this? I'm going to show you some examples now, but you understand this point. Okay, so the last 2 columns, they have to be numbered 1, 1, then 1, 0. Okay, right. Before I give you an example, notice that this row here, this row inside the Karnaugh map, the value of x equal to 0. So what is really common is x prime. In fact, if I would like to combine these 4 midterms, I'm going to get x prime. So I can actually combine these 4 midterms into just a single variable, a single literal, which is x prime. These 4 here can also be combined into x equal to 1. So notice that x is common, y and z differ, and therefore you can combine them into x. Okay, so the first row corresponds to x prime, the second row corresponds to x. Students, are you with me? Please interrupt me and raise questions. Yes. Okay, this is the time to raise questions. Right. Yes.
Do we combine all of them or just the adjacent one? So 0, 0, and 0, 1. And then
if you have 4 adjacent ones in the same row, you can combine 4. So not only you can combine 2, you can also combine 4. I'll show you examples, more examples in the next slide. So the observation here is that in the case of row 0, this will be x prime. And in the case when the row 1 here, x is equal to 1, this will be simply equal to x. And the observation also, if I would like to erase this, notice that here for these, I can combine these 4 squares. So for these 4 squares, I have y equal to 0. So notice that we have y prime, y prime, y prime, y prime. So if you combine them, you get y prime. And it does not depend on x, it does not depend on z. If I combine these 4 adjacent squares, you get y. Notice that you have y, 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 and y. So the values of x and z can differ. It could be actually x prime or x, you can have z prime or z. But the value of y is the same. So therefore, if you simplify, if you OR them, and you use the properties of Boolean algebra, you can simplify this to just y. Let me erase this again. If you combine these four in the middle, so notice that the value of z is equal to 1 here. Notice that we have z, 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 and z. So z is common. And then if you take the distributive property and you combine, you have actually x and y vary. You can have x prime, you can have x, you can have y prime, you can have y, but eventually we'll get z. So you can combine them into z. And finally, these four, which are, you can combine these four, which are on the boundary. So what is common between them is z equal to 0 here is z prime. So if you combine them, you get z prime. Notice that you have z prime, z prime, z prime, and z prime. Okay, so this is something to observe. Okay, when you combine squares, you can combine 2 adjacent squares, but you can also combine 4 adjacent squares if these are midterms. They actually have the values of 1s. Right. Yes, yes, go ahead.
Yeah, what does adjacent mean? The word itself?
Next
Like
to
next to each other?
Yes.
Ah, okay.
So let us now simplify a 3-variable function. So I'm going to now write the midterms, a list of midterms. This is the function f, which is given by this list of midterms in sigma notation. I can write it algebraically. Notice that this is midterm 3. This is midterm 4. This is midterm 5. And this is midterm 7. If I write it as the sum of midterms, I'm going to get 12 literals. But the idea is to use the Karnaugh map to simplify this function to a minimal sum of product expression. Okay, that's really the idea of the Karnaugh map. So we're going to draw the Karnaugh map. This is the first step, is to draw the Karnaugh map and to mark the ones inside the Karnaugh map squares that represent the function f, the midterms. So we have only 4 midterms, 3, 4, 5, and 7. That's the most important step, is to draw the Karnaugh map, because if you don't draw it properly, then everything else will become wrong. So make sure that you insert the ones, the midterms, inside the Karnaugh map properly. So this is midterm 3. This is 4. This is 5. And this is midterm 7. Do you agree? If you cannot really see that, look at the value of x, y, z. So here x equal to 0, y is equal to 1, 1. So we have 0, 1, 1. That must be 3. This is 1, 0, 0. So this square here is midterm 4. This is 1, 0, 1. That must be midterm 5. And we have 1, 1, 1. That must be midterm 7. Okay? So what you have to do is that you have to draw the Karnaugh map. Notice that the column 1, 1 appears before the column 1, 0 in this order. If you don't put 1, 1 before 1, 0, then the entire solution is wrong. Okay, it's incorrect. So the entire Karnaugh map will be incorrect. So make sure that you write the correct solution. You draw the correct Karnaugh map. Okay. So the most important step is to draw the Karnaugh map properly and to fill the ones inside the Karnaugh map properly. Right, now we have done it. We have the Karnaugh map, we have the ones. All what I have to do is that I need to combine adjacent squares. So adjacent means next to each other. I can combine these two. I can combine these two. I can also combine these two. But really, these two here are not really needed. Why? Because it's already enough that to combine. Okay, I already have combined. So the important thing is that to cover all the ones of the function. So this one here, okay, let me just put it like dots, is not really needed because I already have covered all the 4 ones, all the 4 midterms of the function. So if you would like to, let me show you again, erase all the ink. So if you combine these 2 ones, it will be combining minterm 3 with minterm 7. So it will be x prime yz or xyz. We can see it, okay, in the Karnaugh map. So you can see that yz is common. What is different, you have here x prime or x, but x prime or x can be simplified to 1, so therefore you get yz. Now notice that these two minterms, okay, they differ in x. You have x equal to 0, x equal to 1, but what is common is yz. Yz is equal to 1 and 1. So you can get the term directly from the Karnaugh map, and it must be y and z. So we have combined two minterms into a single term, which only that has only two literals, y and z. So that's good. So we had two minterms that had 6 literals, and we were able to reduce them to just 2 literals, just one term with two variables here, y and z. I can also combine these two, okay? Notice what is really common is that x is common, x is equal to 1, and what is also common is that y is equal to 0. Okay, for these two minterms that exist inside this blue box. So they differ in z. So if I would like to write the minterms, this is minterm 4 or minterm 5. So algebraically, this is minterm 4 here. This is M4. This is M5. I'm writing them algebraically. So notice that xy prime is common. Here I have xy prime. Here I have xy prime. And then I can write it z prime or z, and this can be simplified to xy prime. And as I said, you can get x prime, xy prime, x and y prime. You can get it directly from the Karnaugh map. So x is equal to 1, so that's x, and y equal to 0. You can see that y equal to 0 for these two minterms, so that's y prime. So it is x and y prime. That's my term, okay, when you combine these two adjacent squares, these two minterms. So now my final function can be written f is equal to xy prime or yz, and we have simplified it to only 4 literals. So only 4. Okay, is this clear? So we started with 12 as a sum of minterms, and we were able to simplify it to only 4, and we have covered all the 4 minterms of the function using the blue box and the green box. Okay, yes, Ziad, تفضل.
Doctor, can I guarantee after using the Karnaugh map, can I guarantee that the form is the simplest in the simplest form?
Yes, yes, yes. You can guarantee using the Karnaugh map, if you have used it properly, that your sum of product expression, this is a sum of product, not a sum of minterms. So this expression here for f is a sum of products. You can guarantee that this expression, this sum of product expression is minimal. Yes, Ahmed?
Is there any situation, for example, where I have one where a square is alone, where I can't combine it with another?
Sometimes, yes. You might actually have a square that cannot be combined with adjacent ones. So you have to write it as a minterm. Yes. Okay. You might also have this kind of situation. Of course, definitely. Fine. So now here's a second example. Okay, so we have a different function that has again 4 minterms, minterm 3, 4, 6, and 7. And I can write it algebraically as shown here. It will have, this will be a sum of minterms. It will have 12 literals. So the first thing to do is that to draw the Karnaugh map and to learn the locations. So this must be minterm 3. So I'm going to write here M3. Okay, this is M. This is M4. This is M6 here. And this is M7. Okay, so you have to learn where are they located inside the Karnaugh map. Again, 1, 1 appears before 1, 0. So we go from 0, 1 to 1, 1 to 1, 0. Okay, in this order, the columns. So you have to learn where are your midterms inside the Karnaugh map. Then what you have to do is that once you have drawn the Karnaugh map properly, you have to combine the adjacent squares. So these two vertical adjacent squares, midterm 3 and midterm 7, are clearly adjacent, and we can combine them. Okay, so we can write it. This is midterm 3. This is midterm 7. So you can see that YZ is common, and they differ only in X. So we have X prime or X is equal to 1, and therefore I can simplify it to YZ, as we have done in the previous function. The same thing here. But the interesting thing is that these two corner squares are also adjacent, because 0, 0 and 1, 0, okay, they differ only by a single variable, which is y. Z is equal to 0 in both cases. So this is midterm 4 and midterm 6, which are on the corners. I'm just surrounding them. I'm putting them inside the blue box, okay? So I can combine them. So when you look at midterm 4, this is midterm 4 here. This is midterm 6. So notice that xz prime is common. So they have the same x is equal to 1, and they have the same z prime, z equal to 0. That's z prime. And they differ in y. So y prime or y, according to Boolean algebra, this is equal to 1, and therefore we can simplify it to only xz prime. You can also see that clearly from the Karnaugh map that x is equal to 1 and z is equal to 0. For these two midterms, look at z. Z here equal to 0 and z is equal to 0. So that's the same, z equal to 0, so that's z prime. So it is x and z prime. You don't really have to show it algebraically. You can get the term directly from the Karnaugh map. That's the nice thing about the Karnaugh map. And now all what you have to do, you have already covered these 4 midterms. Now you can combine 6 with 7. Here you can combine these two, but this will give you an extra term. So there is no need for this extra term because you have already covered these 4 midterms inside the Karnaugh map. So we have covered all of these 4 midterms. So adding an extra term will not make your function minimal. So now my function can be rewritten as xz prime or yz, and it has only 4 literals. So we started with the sum of midterms. It had 12, and we're able to simplify it to only 4 literals using the Karnaugh map technique. Okay, so everything is fine? Everything is clear?
Yes.
Okay, so we have seen that by combining squares, we can reduce the number of literals in a product term, and therefore we can reduce we can minimize the expression and reduce the cost of the circuit. If you have a 3-variable Karnaugh map, the one square will be a midterm, and each midterm will have 3 variables or 3 literals. If you combine 2 adjacent squares, which are next to each other, and they are ones, yani 2 adjacent midterms, then we can reduce it to a 1 term that has only 2 variables. And if you combine 4 adjacent squares, okay, so you have to be always either 2, 4, or 8. Yeah, it has to be always power of 2. So if you combine 4 adjacent squares, then you can reduce it to a single variable. And if you combine all the 8 adjacent squares, and if they are all ones, then the function will be the constant equal to 1. It does not depend on any variable. So there will be no variables. It will be just the function f is equal to 1 if all the midterms are all ones. Right. This is another example. This is a function that has 5 literals. And notice that if I would like to write it as a sum of midterms, I'm going to get how many literals in this sum of midterms expression?
15.
Yes, thank you. So 15, it's actually 5 times 3. So let us see how we can use the Karnaugh map to simplify this function. So the first step is to draw the Karnaugh map. So I'm going to put here small number here 3, indicating that this is midterm 3, this is midterm 2. This must be here 5. This is 6. and this is 7. Okay, so these are the locations of the squares inside the Karnaugh map. This is how you can locate them. So it's very important to draw the Karnaugh map properly. Now, can you tell me that which ones can be combined? Can we combine 4 adjacent squares? So we try to maximize the size of the box, how many squares can be combined together. Can I combine 4?
Yes, you
Yes.
can.
Okay, so you can see that visually, okay, from the Karnaugh map. This is the beauty of the Karnaugh map, is that it can show you this very clearly. So you can combine these 4. Okay, so these are minterms 2, 3, 6, and 7. If I would like to combine, okay, I still have one minterm here, which is minterm 5, but I need to combine it with minterm 7. So therefore, when you combine, you can simplify. So therefore, the term here will be, this red one will be y, and this blue one here, this will be x and z. I can get it directly. You can see that x is equal to 1 and z is equal to 1. You can see that here we have z, here I have z. So it is x and z when you combine minterm 5 with minterm 7. So therefore, we have simplified this function to have only 3 literals. F is equal to y or xz. Now, algebraically, I need to clean up again. I'm always writing a lot. Does it bother you if I just write a lot and, well, this is actually clear for you?
No, it makes clear.
That's great.
Makes it
Okay.
better, actually.
Okay, good. So notice that if I would like to combine these 4, and here I have minterm again. This is minterm. This is 2. This is 3. This is 6. And this is 7. I'm just putting a number here that will indicate that the index of the minterm. So if I would like to take them algebraically, okay, so these are the minterms here. Okay, so we have here minterm 3, minterm 2, minterm 7, and minterm 6. So what I can do is that I can actually prove it that this will be equal to y, okay, using basically the properties of Boolean algebra. So here I can see that x prime y is common. So I can take it x prime y. Z or z prime will give me 1. So this can be simplified to x prime y. The same thing here, I have xy is common. So again, z or z prime, this will give me 1. So therefore, we can simplify it to xy. And what is common is y. Here we have, sorry, x prime or x, which is equal to 1. And therefore, everything can be simplified to y. Now, notice that for these 4 minterms 2, 3, 6, and 7, you can see that y is equal to 1. So that must be y. It does not depend on z because z can be 1 or 0, and it does not depend on x because x can be 0, it can be 1. So therefore, the only thing which is in common for these 4 minterms is y is equal to 1, and therefore we can reduce, by combining these 4 adjacent squares, we can reduce it to a single literal, a single variable here, which is y. Okay, so that's my algebraic this is my proof, okay, that algebraically we can simplify this to a single literal. We can get this directly from the Karnaugh map, but we can also show it algebraically that you will get this term, which is y. Here's another example. I will continue giving you more and more examples until this becomes clear. But of course, this is all in your textbook. And in your textbook, you will find plenty of exercises and many examples by the author. And what you need to do is just you need to practice, because soon we are going to have quiz number 3, which is related to Karnaugh map. And you need to practice this. Of course, you are going to encounter this also in the midterm exam with a great details. So therefore, the more you practice, you can master it, and therefore you can really get full marks, okay, in the quizzes and in the exam. Let us draw the Karnaugh map. This is my first step. Again, this is midterm 0. I'm going to write a small m0 here. This is midterm 1. This is midterm 2. Here I have midterm 4. This is midterm 6 here, and this is midterm 7. So you have to locate them inside the Karnaugh map. This is very important to recognize. Okay, so to write the ones inside the Karnaugh map, that's the most important thing. Again, I cannot really emphasize this more, is that 1-1 has to appear, column 1-1 has to appear before column 1-0. Okay. Fine. So now you tell me that which ones can be combined, which midterms can be combined from this Karnaugh map.
We can combine
0 and
M2 with
We can combine
M2 with M0 and M1.
so M2 with M0 and with M1. The problem is that I cannot combine 3. It does not really work.
Okay.
You have to combine either 2 or 4.
M0 and M4 and M2 and M6 together.
Oh, this is good. So basically we can combine 4, which are on the boundary. Yes. So think about this Karnaugh map as wrapped around. So column 00 and column 10 are also adjacent. Yani those which are on the boundary are also adjacent. Yes. So I can combine M0 with M2 with M4 with M6. Correct? So I can combine 4 midterms. Okay, we still have some midterms which are uncovered, which is midterm 1 and midterm 7. So what do we do about them?
Combine M7 with M6.
M7 with M6, yes.
And
M1 with
M0.
exactly. So those which are not really covered, we have to cover them. So we have to combine M1 with M0 and M7 with M6. So that's basically the solution. That's basically the solution. So the solution is to combine adjacent squares and try to make the size of the box as large as it can be. So by combining the 4 adjacent squares, can you tell me what is the expression for the red box by combining M0, M2, M4, and M6? So what will be the
Z prime.
Z prime? Yes, thank you very much. It will be Z prime because Z is equal to 0. This is what is common in these 4 midterms. How about the green box?
X prime, Y prime.
X prime.
Yes, thank you very much. And how about the blue box?
X,
X,
Y.
Y.
X and
Y.
yes. We have the red block, which is Z prime. We have the green block is X prime, Y prime, and we have the blue block, which is X and Y. And therefore, this is my minimal sum of product expression. It has only 5 literals. Now, how many midterms do we have here? How many do we have? We have 6, right? So if I would like to write it as a sum of midterms, I will get 18 literals, but I was able to reduce to 5. I can guarantee that this is a minimal sum of products. Muhammad,
Sir, why did you say that we can't add M2, M0, and M1?
Because you see that in order to minimize, okay, when you take 2 terms, okay, already we have covered M2, right? We have already combined M0 with M2, with M4, with M6. You cannot combine 3. You have to combine 2 or you have to combine 4.
Oh, yes, right. Okay.
In the case of the Karnaugh map.
Mm-hmm.
Adham, you have a question?
Yes, Doctor. What if we have in this map only M1 and M6 and M2?
If you have M1 and M2 and M6, you can combine M2 with M6, but you cannot combine M1 with anything. So therefore, you have to write M1 as a midterm because it cannot be simplified. Okay. But you can combine M2 with M6 and you can simplify. Okay. Fine. So what you have to do is just you have to practice. There are many examples. Of course, you can get different functions, different midterms. Or what you have to do is just draw the Karnaugh map and minimize. Ziad, you have a question?
Yes, Doctor. Can't we combine M1 with M7? They both have Z.
You cannot combine them if they are they differ by 2. Okay, so you can see that you cannot. M1 and M7 are not adjacent.
Should be.
So you cannot go diagonal.
Oh.
The reason is that M1 and M7, they differ by 2 variables. You can see in M1, you have X is equal to 0, you have Y equal to 0, and Z is equal to 1. So it is X prime, Y prime, Z. That's M1. Notice in M7, you have X is equal to 1, and you have Y is equal to 1, and Z is equal to 1. So therefore, they differ in X and they differ in Y. They differ actually in 2 variables, and therefore you cannot combine 2 minterms if they differ in 2. So they are not really adjacent. So diagonal. So if you look at 2 squares which are only diagonal, they are not adjacent. Okay. So they have to be either, you can combine them if they are in the same row or in the same column, but not diagonal. Okay. Let me talk about 4 variable Karnaugh map. So I talked about 3 variable. Now we would like to go to 4 variables. In the case of 4 variables, we'll have 16 squares. And these are numbered from 0 to 15. And we can draw it as 4 by 4, 4 rows and 4 columns. Okay, so the variables here are called W, X, Y, Z. We can call them also A, B, C, D. So we use WX for the rows, we use the Y and Z for the columns. Again, row 1, 1. So we go here 0, 0, 0, 1, then 1, 1, then 1, 0. So notice that 1, 1 appears before 1, 0 in this order. Okay. The same thing for the columns. Y, Z, 0, 0, 0, 1. Again, 1, 1 before 1, 0. Again in this order. And the reason why we put 1, 1 before 1, 0, so that the adjacent squares will differ by the value of a single variable. Okay. So now we have, okay, we have 16 entries inside. So we have 4 by 4 Karnaugh map. So this will be like 16 entries in the truth table. And these are the midterms. So we start here 0, 0, 0, 0. That must be midterm 0. So this is the square here for midterm 0. Then 0, 0, 0, 1. This will be midterm 1. Then we have 0, 0, 1, 1. This will be midterm 3, then midterm 2. In this order. Then 4, 5. Notice that you put 7 before 6. Okay, according to how we number the columns. Notice that M8 appears here. It is 1, 0, 0, 0. That's M8 in the last row. Then 9. Notice that 11 before M10. And then we have 12, 13. Here we have 15, then 14. So this is basically the locations of these minterms inside the 4 variable Karnaugh map. So you have to remember, okay, you have to remember where are the locations of these minterms. Any small mistake means that your problem is gone. So you have to make sure that there are no mistakes. Once we have the 4 by 4, so we have the 4 variable Karnaugh map, we have 4 rows and 4 columns. So these are 16 squares. If you have 1 square, it will be a minterm with 4 variables, as we have seen here in this slide. So each minterm will contain all the 4 variables, like minterm 0 here, okay, W prime, X prime, Y prime, Z prime, and midterm 15, which is W, X, Y, Z. Okay, so you can see that all the 4 variables, if they may or may not be complemented, with prime or without prime. So these are 4 variables or 4 literals. Okay, they are called literals. Right. So if you have 1 square, it will be a term that has 4 variables. If you combine 2 adjacent squares, now this is interesting. If you combine 2, then you will get a term, not a minterm, a term that has 3 variables. If you combine 4 adjacent squares, you will get a term that has 2 variables. If you combine 8, you will get a term which is just 1 variable. And if you combine all the 16, all of them actually are all ones, then the function will be the constant 1. It does not depend on any variable. Okay, this is basically how we use the 4 variable Karnaugh map. So I'm going to show you some examples. This is basically combining 8 squares. Now you tell me, okay, so notice that how I'm labeling here the rows and the columns. So notice that here that for these 2 rows, you can see that W here equal to 0. So this is actually labeled as W prime. Here, these 2 rows are W equal to 1. So this is W. Now for the 2 columns here, you can see that here Y equal to 0, Y equal to 0. So for these 2, this is Y prime, this is Y. These 2 will have Z, and these 2 which are on the boundary, this will be Z prime. These 2 in the middle are actually X is equal to 1. You can see that X is equal to 1 here. Whereas these 2 which are on the boundary here, this and this will be X prime. Okay. Fine. So this is my 4-variable Karnaugh map. You tell me, what is this? If I can combine 8 squares, if I combine 8 adjacent squares, what's the term? This is
W prime.
W prime. Exactly. The term is W prime. If I combine these 8 adjacent squares, what do I get?
Y.
It's actually very clear. How about if I combine these which are on the boundary? So column 0, 0 with column 1, 0 is what?
Z.
Y prime.
Z
G
prime.
prime.
Z equal to
Z
0.
prime,
Yes,
yeah.
so Z prime. So this is basically how we can combine 8 adjacent squares inside the 4-variable Karnaugh map. Let us combine 4 squares. So let us take this. These are 4 adjacent squares. So what will be the term?
X, Y prime.
It is X and Y prime. Yes, thank you very much. How about these?
W, Y. Or Y,
It's
W.
W and Y. Yes, thank you very much. How about these, which are the 4 on the corners? The 4 on the corners are adjacent, by the way. They can be combined.
X prime and Z prime.
Okay, good. So now you are getting it. So it's actually X equal to 0 and Z is equal to 0. So it must be X prime, Z prime. Okay. Now, even if you don't really label that W, you see that even I don't really write here in red the W prime, W, and so on. Look at the values of these variables. Notice that here on the corners, you have X is equal to 0. This is X equal to 0. This is X equal to 0. Notice that here Z equal to 0. Z equal to 0. Okay. So what is common for these 4 midterms is that X equal to 0 and Z equal to 0. So the term is X prime and Z prime. Okay. Let's combine 2 adjacent squares. How about these 2?
W prime, Y prime, and all it
And
is.
what?
W
And
prime
X.
X Y prime.
So W prime and X and Y prime.
Y prime.
Exactly. So you see that we have W equal to 0. So that's W prime. X is equal to 1. So that must be X. And we have Y equal to 0 for these 2 midterms. Y equal to 0. So that must be Y prime. It does not depend on Z. So notice that by combining 2, the less you combine, the longer is the term. So now it has 3 literals, 3 variables. So W prime and X and Y prime. How about combining these 2? Please quickly.
W prime Y Z.
Again, say it again.
W prime X Y Z. W prime Y Z.
YZ. Yes, thank you very much. How about combining these 2?
W Y prime Z.
Okay, thank you very much. How about these 2 which are on the boundary, on the corners?
X prime, Z
W
prime.
Start with W.
W X prime and Y prime.
Okay, good.
No, Z prime.
Z prime.
Okay. So it's not Y prime, it's actually Z prime. Okay, make sure you don't really make this mistake. So what is common is actually Z equal to 0. Right. So now let us take a look here at simplifying a 4-variable function. So now I have 4 variable. Okay, so I have to draw here a Karnaugh map that has 16 squares. So in the case of 4 variables, you can go from min term 0 to up to min term 15. Of course, if I would like to write this as a sum of min terms, can you tell me, okay, if I would like to write this function as a sum of min terms, how many min terms do we have here? 1, 2, 3, 4, 5, 6, 7, 8. And each min term has how many literals?
32 literals.
4.
So it will be 8 multiplied by
4.
By 4, which is equal to
32.
it will be a long expression. Okay, so this is why we will not really write it as a sum of min terms. We need to simplify this. So I'm going to draw the Karnaugh map, and the most important step is to draw the Karnaugh map properly, to fill the ones inside the Karnaugh map properly. Any mistake means that you did it wrong. It's not the function. So notice that this is min term 0. So I'm going to write a small 0 here in the corner. Okay, this is 2. This is 4. This is 5. This is 6. And this is 7. And this must be 8 here. And this is 12 here. Okay, so this is their locations. Now, can you tell me which ones can be combined?
0 and 2 and 4 and 6 for one block.
Okay, so you'd like to combine 0 with 2 with 4 and 6. Okay, fine. Which ones can also be combined?
4, 5, 7, and 6.
Yes, and which ones can also be combined?
And 7
Sure.
and 6 and 4.
0 and?
4 and 12 and 8.
Yes. So basically, these are the ones. So we're going to combine. So what will be the term this for green? This green block. Can you tell me what's the term?
W prime X and
so it's W prime and X, and that's it. There's nothing else. It is just actually 2 literals, because it does not depend on Y and it does not depend on Z. How about this one, this red block?
Y prime, Z prime.
Yes, simple. And as you said, we can combine, okay, 0 with 4 and 2 and 6, which are on the boundary. So let us combine them. Okay, now the more you combine, the better. Okay, you should not really combine 2. If you can combine 4, okay, you should really combine the 4, not just 2. Okay, so what is this, the term for this blue block?
W prime, Z prime.
Okay, so what is common is W equal to 0, Z equal to 0. So it must be W prime, Z prime. Thank you. And therefore, we can write the expression. This is my solution. This is a minimal sum of product expression for the function f. It only has 6 literals, not 32. The sum of minterms has 32, and we're able to simplify it to 6 without the need to use any Boolean algebra. We got this expression directly from the Karnaugh map. You see how useful it is and so easy to use? Yes, Sally.
Doctor, there is overlapping. When do I know that it is okay to reuse this square and when it is not okay? For example, 5 and 7.
Yes.
Why we don't combine them?
We are combining them, but if you combine them, even if you are actually have already combined them, okay, with already ones that have already been, even if there is an intersection between 2 blocks, that's okay. And the reason why we have these is that to minimize the term. And I could have combined 5 with 7 without combining it with 6 and 4, but this would result in a longer expression. So the purpose is to cover all the ones inside the function. Okay, that's the purpose. So in order to get it minimized, I have to maximize, okay, combining squares. Now I can combine 5 with 7 only, okay, but that will give me a term that has 3 variables. If I combine 5 with 7 with 6 and 4, it will give me a term that has 2 variables. That's better. Now the purpose is to cover 5 and 7. But the reason why I'm combining it actually with 4, okay, adjacent rather than just 2, is to minimize the expression. That's logical. Okay, Ali?
Okay, but when do I know that I can reuse this square and when it is not?
I'm going to come to an algorithm, not this lecture, next lecture. And I'm going to show you if you follow this algorithm, you can actually guarantee. I need to talk about prime implicants and essential prime implicants. So what's important is actually to discover these essential prime implicants that exist inside the Karnaugh map. But this will be my topic next lecture. It's a bit early to talk about it now, today in this lecture.
Okay.
Right. So that's an example about simplifying a 4-variable function. In fact, this is just my next topic about prime and essential prime implicants. And then once I cover this, it will become very clear to you, okay, how to choose, how to, okay. So what we need to do is that we need to maximize combining squares. That's clear. But how do I select, okay, these terms, okay, to make sure that my function is minimal? So I'm going to talk about this, inshallah. I need to talk also about minimal sum of, I talked about minimal sum of products, but I need to talk about minimal product of sums. Okay, so we can also obtain minimal product of sums from the Karnaugh map. Yani you can have not only sum of products, but also product of sums.